Collin. Welcome. So we're here to talk about the HypothesesUpdater prototype. Discuss further. Yeah. So what should be the next steps? Like reading your summary, you mentioned that like phase 1 to make sense. Phase 3. Like what are your questions? Right. We only had like 1 or 2 exchanges about it. Anything else we should synchronize on? Or
I mean, in terms of like the overall workflow plan, I think that makes total sense. Start on a different branch or fork. Start trying to develop a GPU backend and CPU backend. Get it all integrated.
Yes. So what I'm thinking is specifically like on your TBP Monty fork, if you create a branch, and then the other thing is if you create a draft pull request with that branch, then me as a maintainer, that allows me pushes to them, and so that actually can facilitate like me adding something, or so like we're actually working together versus just me trying to work through you. And actually say like, hey, how about this commit? How about this commit? So that might be helpful.
So
but I think that
in my fork, create a new branch and go ahead and start a pull request, and we'll just kind of work through that pull request flow.
Yeah, as a draft, because that would allow. So that would allow. I believe if we look at like a pull request that we have, what's an external pull request? Here's one of them. Okay, here's an external pull request. So over here, there's their maintainers are allowed to edit this pull request, and so I think it gives me branch permissions to the branch. I mean, can we try that? Actually, let's just try it, see if it works. We could just make a branch, make a pull request, see if I can push to it. That'd be a nice experiment.
Yeah, definitely give that a try.
Start presenting.
Do you want me to do that now or follow up after?
I was gonna say, do you think it's a good use of time?
I have some things I want to talk about.
Okay, let's talk about that.
So maybe we should prioritize.
Let's do that. Cool.
Yeah. Let me share my page. Yeah. So I just kind of started making a little document to talk about. Okay. Getting used to the Google Meet workflow.
So I can see your ID.
So anyway, the key thing I wanted to talk about, because basically, when I first proposed this, I was looking at trying to batch operations across LMs. And in that kind of initial post in the comments with Vivian, she was suggesting that keeping the kind of LM more separate is more conceptually better, and because at runtime it's actually not easy to predict exactly like which LMs will get what inputs at different times, so it might have some more complicated structure to try to batch across LMs. So that's what led me to kind of think about doing this different CUDA streaming approach. And so I started trying to outline that also in the in the comments on the separate post that you created. But I think that's where it would just maybe start to change a little bit of the the interface between like the Monty experiment and the LMs to the hypothesis updater.
Okay.
So the key thing here is, well, actually, okay. Do you feel like it'd be helpful for me to explain what a CUDA stream is, or do you get that from the post I made?
I think I get it. I think I would get it out from context.
Yeah.
If you want to, you're welcome to.
No,
I think I'll.
Let me know. Feel free to ask questions if I.
It's like a CUDA thread that runs in parallel, but basically you can put kernel operations per stream.
Yeah, and so it would benefit because we can, in the code, kind of keep the LMs more separate. They could launch the same kernels, but just with different inputs, or slightly different kernels. Like, they can all do that fine on their own stream. But the GPU itself can actually schedule work, from all of the different kernels across all streams that has available. And so it can kind of do it, GPUs are designed to have really complex scheduling to maximize throughput, right? So, if one warp in one kernel, starts a memory access, that's going to take hundreds of cycles, right? It'll just switch that out for a different warp that has compute work that needs to be done, right? So, I mean, GPUs are designed to just kind of fly through all of the work that they have stacked up. And so we would still benefit from parallelism across the LMs, but it would keep them kind of defined separately and allow for a little bit more variation in behavior. I know you were saying kind of in response that, like, based off of the data flow diagram that you outlined, I mean, we want LMs to all be doing the same operations at the same time. We don't really want kind of different flows for the different LMs.
I maybe misspoke about the same operations, because that presumes that all LMs are the same implementation, right? But they could be different implementations. The internals of an LM could be different, right? Like one of them could be the current one, feature graph LM, but another one could be LM using like grid cells and whatever, and we're trying to compare them, or we have a mix of them. So I overconstrained and misspoke. It's not that the same operations, but that are all going through the same phase. But each one could have different operations.
Right. Yeah, that makes sense.
And by phase, I mean they get inputs and they need to produce outputs before moving on to the next phase. That's what I mean.
Yeah, no, that makes total sense. I think even in my original kind of ideation of the stacked implementation, we would kind of group LMs based on their type and or input. Kind of, I didn't really figure out the details about whether they all need to have the same input for the kernels, but that would also be a little bit more complex to add that overhead of figuring out kind of how to group them into the proper buckets, right? That could be stacked. And so CUDA streams just avoids that complexity. So yeah, we can have different types of LMs processing different inputs, or like you say, like some could be doing no ops, or just like other kernel operations, and we could still benefit from some parallelization. It'll be less than if we stacked it. Like, that's the most efficient way to do it. But I think the flexibility that comes with it, I do think that's I think it's a better approach for Monty. Like, I think that maps to the existing architecture better. But what comes with that is basically we need to switch from sort of the sequential blocking loop that we have right now for how we process hypothesis updates to a non-blocking call. So right now, the Monty experiment will loop through each LM and call the updates, wait for that to finish, and then go to the next LM, right? We wouldn't benefit from any parallelism, even if we use CUDA streams, if we did that, because one stream finishes before the next one begins. So basically, we would just need to switch to something that's basically got dispatch phase, right? So I mean, we can obviously work out the details more. This is just kind of a quick pass of the basic structure. But we just wanted to launch the kernel update, or launch the pipeline kind of kernels for each LM, and then return immediately. Right, so it actually goes through all of the LMs and dispatches the kernels, and then some sort of kind of synchronization waiting phase while that work completes, and the Monty experiment kind of knows not to do anything until that's done. But once it gets that update that it's done, it can then read the results, move on to the other steps in the experiment. Right. I think it's a pretty common pattern, pretty straightforward. But it will just require a little bit more refactoring of the code. Like, I was starting to kind of take a look at the different calls through here. So I mean, like step learning modules. Right now would just call this LM step method. Instead, here we'd need to do like a dispatch step, and then kind of maybe rework some of the logging and such out of this, and then do a kind of a wait, and then
so one thing immediately pops up here is the dispatch step. Like, aren't we getting? Yeah, because we still getting sensory inputs for every LM, right? Line 81.
Sensory inputs.
Collecting.
Yeah.
But that's still done in series to collect those inputs.
Yeah, so I think
then,
yeah, we'd have to kind of figure out exactly what operations are worth parallelizing. Yeah, I didn't really look into sort of the details of some of these other pre-processing steps. If they're pretty quick, it might not be worth the time, but we could also look into whether we can parallelize more of the pre-processing and kind of do the full pipeline.
I guess I'm just wondering if like the parallel switch should happen at the step learning modules level. Like it's an alternate step learning modules implementation as opposed to reusing it and swapping out calls in parallel sort of thing. That's kind of the question that I have.
Yeah, so like instead of having the loop over learning modules in step learning modules, like we do this kind of a level up from this function.
No, what I mean is okay, I see what you're saying. This is why you're talking about non-blocking, because the dispatch step will add a non-blocking call. And so if we have a CPU backend, you can still do the same thing. You just essentially collecting it later. Where you collect where's the gather
Yeah,
step?
so I mean, this in a super super high level that I was doing right before this.
Yeah.
I kept like the same code just to kind of see where it would insert. But basically after that, you'd want these calls to all return so that the loop finishes before any of this work is actually done. All that happened is a dispatch. Then you probably just have a blocking call after that. So once all of the LMs have dispatched, we just wait until they're all done. There's more complex ways we could do it too, right? Like as soon as one LM finishes, you go ahead and start with some of the work. But I think that could come later. I think it's much more simple to just wait for the backend to say that it's done processing all the work. And then you can kind of go ahead with the rest of the code as normal. You just need to add some call to read the results back from the backend, because that would also probably, that will need to read the whatever results you want, right? Like, whatever hypothesis values or everything, you have to actually read that from GPU memory back to CPU. So you want some sort of explicit read call, and then you can do the rest of the code.
Okay, yeah, so scatter, block, scatter, and then block, and then gather. Okay, yeah, that makes sense. I'm just, and this is step learning module. Okay, got it. Because that allows us to. Okay. Yeah,
and
that's helpful.
I mean, certainly the Monty code better than me, right? Like I was just kind of going through and following the functions, and at least for the experiments I was running, to get a sense of where everything is happening. It seems like this is, because this is where the looping over the learning modules happens, kind of where we would start with adjusting how we dispatch the work.
So would it be helpful to you? So I'm just thinking about more generic processing, like if in case you did want to stack things together, right? Because with this approach, dispatch step is pretty much, if I'm understanding correctly, a dispatch step will create a GPU. Was it stream? Was it?
Yeah, a stream.
So dispatch step as a stream. Is that what the outcome of a dispatch step is?
So I actually think, because, correct me if I'm wrong here, but my understanding is it's a pretty set pipeline of operations for the hypotheses update steps.
I guess what I'm asking is, you said that stacking things can be more efficient than adding streams. If we want to stack things, then we would probably want, if you scroll up, if you want to gather all the sensory inputs all at once and have a set of sensory inputs and LMs, and then stack them together and then dispatch that stream, right? That would be.
Yeah. So when I was saying stack them, like that's in like my original kind of proof of concept code, where we're actually doing one kernel dispatch for each step in the pipeline for all of the data across all LMs. So in that case, we wouldn't even need multiple streams. Like it would just be one CUDA stream, just one sequence of kernels.
Right.
and just one kernel dispatch for the entire operation.
Yeah.
And that would be more complex because we would have to like accumulate all of the data into kind of like one contiguous buffer to pass into the kernel. And so there's some overhead, right? Whereas with this CUDA stream approach, because each stream is kind of handled separately, has different kernel dispatches, you can have different references to the memory objects and everything. It's much simpler to implement, but it might be less efficient because you're dispatching multiple kernels, right? Which might have their work parallelized by the GPU scheduler, but you're not actually defining, like thread level parallelism by doing one giant kernel dispatch that can just do it all in one go. Does that make sense?
Yeah, that makes sense. And the reason I'm poking at this is because if we're going to change the API, I'd rather change it once than change it now and then be like, oh, yeah, and we want to add stacking and we have to change the API again.
Sure. Yeah.
And so that's what I'm saying is, even if in this initial step we're not doing any stacking, I want the API, like I want the swappable backend component to the API for that to support stacking if we want to add it later.
Yeah, no, that makes total sense.
So that's why I'm looking at like, okay, so in this, as you wrote it currently, this is super helpful because it like allows me to completely understand what you're talking about. So in this implementation, we wouldn't be able to do stacking because we're dispatching could a stream correct my vocabulary, please?
Dispatching a different, like a kernel on a different stream.
Okay, so we're dispatching a kernel on a new stream with every dispatch step, right? And sensory inputs are just the inputs for that LM. So we're essentially dispatching a new kernel stream per each LM with just its inputs. And it is my understanding that there may be a future optimization that might be possible where if we were to stack like learning modules that are doing the same thing, do they require for stacking? For stacking, I'm assuming that just the kernel needs to be the same. The inputs would just also get stacked. Is that true?
Yeah, so it would be, like a step where we put all of the inputs, stack them into one input buffer, and then just launch one kernel. Yeah. So
that API would require multiple sensory like a vector of sensory inputs and not just sensory inputs for this LM. So we would have a vector of sensory inputs and a vector of LMs. And then in the current implementation, it could always be just the one, like vector of, like we can always, it's the batching rule. We can always have a vector of one, but it's hard to introduce a list late after the fact. But that's kind of what I'm thinking about this API, where it becomes where to make the breaking point.
That's good to consider that. I mean, also, if we're actually stacking all of the operations across all LMs, we also wouldn't have to do this sort of like 3-phase approach where you do dispatch, blocking wait, and then read, because we just have the one pipeline, right? So you just dispatch a kernel, and then once it's done, read the results. But kind of like we were saying, we might have to do kind of different subgroups, right? Like we might batch LMs of a certain type together, or ones processing different inputs, in which case maybe we would still sort of need a some level of a sort of dispatch step, right? Or maybe each group of LMs that are processing together run on one stream. So I don't know. It would kind of introduce this level where we separate LMs into different groups, and then you follow this kind of same dispatch API.
Right, and it could be as simple as, and this is why I was thinking, and if you scroll up a bit, why this backend might be involved with, like, where do we make the interface at? Because it could just be like, here's all the learning modules, here's all the sensory inputs, and then even the GPU initial implementation is just a for loop of single dispatches, right? But it opens up that grouping then would happen in the future, would have to happen inside that API, not before it. Do you think the grouping should happen before? Like, do you have enough information to do meaningful grouping before handing it to the backend, or should the backend do the grouping? I guess that is the question that I'm trying to pose now.
Yeah, I don't know, because I think basically we could group LMs like as long as they're doing the same operations, and we could figure out how to do it with different inputs, right? Like even if they're processing different sensor patches, as long as it's the same type of LM doing the same sequence of kernels,
right.
we could stack them. But like in Vivianne's comments, she was saying, it's hard at runtime to know which kernels are going to be processing which inputs. Like some might, not be processing, the same input, in which case you might not want to include it in the batch. So it does seem like kind of almost per step the grouping could change. I think that's what we would need to figure out, because it'd probably be more efficient if it's more like experiment wide. We can do the grouping at the beginning and then have that be consistent throughout all of the steps, versus if at every step we're like doing a different grouping of LMs. I think that would start to get complex.
And then this is a naive question, but if an LM doesn't have inputs for a no-op, like, would you just zero out the sensory inputs and just or would you just zero out the sensory input? No, because we don't. Would we just ignore the outputs? Would that be more efficient than trying to regroup things?
Yeah, I think zero out, and then you could have a simple case in the kernel itself for like a flag, or if it just sees that, it's like the input is just zeros, it skips doing the work. That would probably be better than doing a whole new grouping if it was just to skip like a no-op for one LM. Yeah.
We ask that because that sort of just handles the not everything will be processing. It's like, okay, well then.
Yeah.
So that would handle that case. So the only other case would be, the other thing is, so LMs, I'm just trying to, this is sensory, this is sensory inputs, but they could get, an LM in the future could get, so as I'm building the CMPV1, right? Like so what can happen is a learning module's inputs. Let me pull this up. So I'm not trying to do this from memory.
Do you want to share?
Yeah, I'm gonna share the screen. What am I looking for? Is the I'm trying to say RFC. Okay, so so this thing, okay. So learning modules received. Okay, so the things that are getting delivered. Okay, so this is what I was trying to highlight. When the inputs into learning modules will be like the outputs from the sensor modules, these are going to be stable. So like once your sensors are hooked up to your learning modules, it's always the same. The difference is the inputs from the previous steps learning modules. What this encodes is a hierarchy of learning modules. So when learning module outputs, it can output 0, 1, or 2 cortical messages, and so it can output no messages. It can output a goal, or it can output a what do we call it now? Percept, like a perception. And so a goal would go to a lower level learning module, and a percept would go to a higher level learning module. Essentially, there's like a top-down goal-driven stuff, and then there's bottom-up, like assembling a hierarchy of inputs. Does that make sense?
Yeah.
So the reason I want to highlight that is the inputs, this will be constant, but the inputs to the learning module actually might be different with, if it gets, because it's going to get a sensory percept, and then it might get a goal from a higher level learning module. And so sometimes it might get no sensation, 0 inputs. It might get percept from a sensor module that's stable, but it also might get additional. There's some bounded count of how many messages, but it depends on connectivity. But so the inputs will be variable with no input, 1 or more. to some finite amount,
Mhm.
but at any step, that width can change.
Mhm.
So I just want to highlight that.
Yeah, I think at a high level that should be fine because we're already envisioning sort of a input processing phase, right, where we stack the appropriate inputs, and I mean, kind of assuming these would be variable sizes.
Yep.
In practice, like when you get into some of the lower level details, right, there definitely could be some overhead by having kind of, particularly if you're stacking, right, like kind of recreating a new buffer and transferring that every time. Whereas if you had like fixed size inputs, you could more easily sort of like pin the memory between the CPU and GPU and just like push to the right place. But it seems like we could even get around that by just over allocating, right? So like if it's a certain max input size and it's not an unreasonable amount of memory or something,
we would know
for each input.
We would know that amount because that is a configured connectivity. So that is defined at the start of the program, and it's like you can only get inputs from the things you connected to. So we will know that. Okay, cool.
So yeah, that's probably pretty straightforward to get around. I think, yeah, it's really just more, figuring out the LM grouping and having that consistent, if the individual input data is changing step to step. I don't think that's a big hurdle.
And I mean, right now, I'm thinking, I mean, LM grouping is kind of by type, right? Like if it's the same class, it's going to have the same implementation, it's going to do the same computations. It's like it should be before the backend. It should be trivial to group these, but like something backend wouldn't have to worry about. So the API could just get the grouping.
And I guess in the simpler cases I was looking at, or just one level of hierarchy of LMs. But to your point, I mean, you guys are envisioning a more complex graph of LMs. We would probably have to do the grouping based off of like when the LM would be processing data. So like the first level would get grouped together, and then if those are kind of passing to like a second level of LMs.
That's not how it's going to work. So any hierarchy messages are across steps.
Right. Okay. That's kind of like the hierarchy kind of thing. So it's like they're all one level and getting it from previous steps.
No, there's still like a hierarchy set up. Well, what I'm let me show a graphic, but it's super helpful for this. Let me just try to find it. How was it? It was, I think, I'll download it and share it real quick. It was a. Here we go. Let me take a screenshot. Put this in here. Okay, cool. It works like this. So when it's getting passed between the levels, it only ever travels so it's at frame 1, that's one step. And even if it goes up the hierarchy, there's travel time. So at step 2, that one LM will receive the previous steps from lower level. And then same thing from top down. So that level L will send down to level L-1, but in the next time. So what you see every step, but what I'm saying is every step, all LMs compute. There's not a hierarchy breakdown inside a step. So it's just like, so every step, every LM gets inputs, every LM puts outputs, and then go on to the next step, There's not like in a step, we're going to do level 1 and then level 2 and then level 3 and pass messages between that. We don't do that in a step. It's not how it's set up. Does that make sense?
Yeah, that makes total sense. So yeah, that would be even easier for the grouping because you can just do like LMs all in one group, regardless of the level.
Exactly. That's why I was thinking that. So that's why the framework can just give you the grouping. So here are the same things. It will compute the same. Okay.
Yeah. So yeah, so I mean, it seems like stacking could be feasible with the system. Like
Right.
it wouldn't deviate too much from the principles and require too many changes. I do think it'd be more complex. I think the CUDA streaming approach is simpler. And I just don't know what the benefits would be, kind of comparing them, right, without profiling data.
Comparing what's the other alternative? Could a
Oh,
streaming
like
work?
doing like the CUDA streaming approach versus trying to stack and do single kernel dispatch for all LLMs.
Okay. I would. So I am not advocating that we try stacking now.
Okay, you just want to make sure we could support that.
I just want to make sure that the API, that we don't have to change the API twice.
Yeah.
And so when you get a group, just well, I guess that's a consequence of that, right? Because that means inside that call, even if you get groups, do you then now dispatch, block, and get scatter, block, and gather in that call, or do you do it across the group calls? I see the.
I feel like could we try to have the API support this idea of an LM group? And for the initial implementation, it's just every LM is in its own group. We're not trying to, if we don't want to support any stacking, but maybe that API would be consistent in the future. If we start to group LMs, then they just become, that group is now a part of that dispatch block read results flow.
Okay, yeah, I see what you're saying. My question is, do you would you want to so if we do the grouping thing, I know we're talking about something we're not going to implement, so I'm sorry.
Yeah.
But if we do the grouping thing, would the approach be then you'd wait for that group compute to finish before starting the next group, or because you're essentially for that group, the implementation would be for that group, stack one GPU stream, dispatch one GPU stream, and then wait for that to finish, or for that group, stack, dispatch that one stream, then grab another group, stack, dispatch that one stream, and then wait for all streams to finish.
The second approach. So basically keep the same idea we're doing now for per LM, and then do that same dispatching scheme, multiple streams, but just have each stream be a group.
Got it. Okay, yeah. Okay, I think I'm now caught up with what you were saying. The API is a list of groups. And initially, it's so I can give you either the list of one group, or I can give you a list of one LM groups.
Yeah.
But it sort of doesn't matter. Okay, got it. But the API, you get a list of groups. Okay.
Yeah. So yeah, at least the experiment level, we can kind of design the flow around that, have a consistent interface. So then the backend, we can start to change depending on whether we do stacking groups or not.
And this allows the backend to use the group if it wants, basically a list of lists. It uses the groups if it wants, or it flattens it if it does not know how to do any. Like, so for the CPU version, we would just flatten it. There's no distinction between this group or that group. So it would just become a for loop of what it currently is.
Well, we might want to do some multi-threading at that level for the CPU.
Okay, there you go. Yeah.
There's some parallelization we could do.
Yeah, but the naive, current approach of we just flatten into a for loop, and that would be the equivalent of. I'm just trying to think of, if you recall, I was saying, sharing screen, this bit, where I was like, the current CPU backend kind of like, whenever we factor it, I want the default implementation to be the current implementation. And so the default implementation of the SAPI will just flatten that list of lists into for loop and be exact the same code, basically.
Yeah.
To start with. Okay. That sounds plausible. I'm sure we missed something that will become apparent as soon as we start running code, and it's like, this will never work.
We're only a half hour in. It's a pretty reasonable one somewhere.
Okay, what else would you like to talk about? Because I feel that's that's not impossible, and seems like we can figure out a way.
Yeah, I mean, the rest of it, I mean, I think it's starting to just get more into like into the weeds about what all we could change. Like I was starting to look at sort of the the stack of functions before you actually reach the hypothesis updater, right? Like the step learning modules, the matching step,
All right.
the compute possible matches update. Like we'd have to kind of figure out how to do all of that in like a non-blocking dispatch way.
That's what I wanted to ask. Like, which kernels work? What is the minimum set of operations? Because for the prototype, we should just use the minimum set just to make sure that it like end to end can run without necessarily trying to make all the kernels work, make the machinery work. So it's like just pick the kernels that are functioning and
yeah. So of the ones that I shared in that post, everything is working except for KNN, with the caveat of a couple are like not quite as consistent. So like the custom distance is accurate to like a tolerance of like, you know, E-2, I think, whereas the others are all to like E-5. And I'm not really sure why custom distance isn't as consistent.
Okay.
There was a bug with the pose evidence kernel, and I fixed that, but it's also now, it just has a slightly lower tolerance for it to pass. So that's, you know.
Gotcha.
But the kernels seem to be functional and like give pretty much the right answer for everything except KNN.
Okay, so that gives the target to what the GPU hypothesis up there can swap, right?
Can you say that again?
That gives a target of what the initial implementation of the GPU hypothesis out there.
Yeah, I think the thing that's missing in my understanding of how well we could drop and replace. I mean, you know, like this proof of concept, I kind of took the core computation, made that work. You know, made it work for the trace data that I was saving through like the profile hypothesis updater. But I feel like there's still got to be edge cases and like control flow linking these computations that I haven't worked through, like how that would all map to a GPU implementation. Like I kind of, once I got to the level of breaking into these different operators, I kind of lived at that level and implemented the kernels.
Yeah.
But some more work would need to go through to actually think about, okay, if we're actually doing the full end-to-end, you know, you give a input, you know, sensor, you know, and then sensor reading, and then final hypothesis update outputs. Probably need to do some work to chain those together.
Is that something you want to do now, or is that something you want to do offline?
Oh, we can start to go through it and talk about it.
Is there anything else you'd rather talk about? Because yeah, I agree. Like, it sounds like we have an idea for the high-level API, and that's still not the thing that you need.
Yeah.
Right. So the thing that you need is actually the nitty-gritty detail of swapping out. Like what object can we swap out, or what we have to change to make that possible, right? Hypothesis updater.
This is just the Monty code base. So So yeah, I don't have a specific question. I mean, I just kind of need to spend some more time going through this and thinking about how everything chains together. But yeah, we can kind of do that right here.
So, because the other thing I'm wondering, like, we have the hypothesis updater. Are all the operations there's? I remember there's, and then is there like one, and then this what's in the, there's some things that are in the displacer and some things that are in the updater, right? But what we're talking about even is we're not even talking about. It sounds to me like we're not even talking about an alternate hypothesis updater. We're talking about actually inside the hypothesis updater, there is a different implementation. Like so it's like,
yeah. I mean, I think this could just be a different hypothesis updater. I think it's up to us to figure out what makes the more sense.
well, the reason I'm thinking is because if you look at resampling hypothesis updater, that's already an alternate implementation, right? And so the question then is, you probably don't want to re-implement a GPU resampling hypothesis updater and a GPU default one, right? And so there is some operate. Did you actually have a chance to look at this and see if it has other?
No.
Okay, gotcha. So that's what I'm trying to highlight.
That it was updated, but I haven't really looked through it yet.
So this does different things.
Yeah. Okay, so yeah, I mean, it would probably make sense then to do like just a different backend for the hypothesis updater, so we can keep the current level of API, right? And then it's really, it's like, when it calls into update hypotheses is where we start having the backend take over and actually do the computation.
Yeah, and I can ask the team, because I don't know off the top of my head whether like resampling one is the feature and just don't even bother with the default because it's going to go away or something. I can double check. Let me make a note to myself.
I haven't really gone through. It's like, what at a high level, what's different about the resampling?
I don't remember off the top of my head.
Yeah.
That's Rami built that one. I refactor a lot of the code, but it was like I was very much from a mechanical software design perspective, not looking in the guts of it. So I have to ask. Well, hold on. Let me just write down. Check if resampling. It might come back to me when I look at it. The resampling hypothesis updater is the feature. Can we not bother with GPU for default hypothesis? Okay. Let me. I'm gonna look on my screen here real quick to see what the difference was. Actually, I'm gonna look at the pull request that introduced this because that probably has a good high-level description of what the change was.
I feel like there was there an RFC for the resampling hypothesis updater?
Oh yeah, probably. Good call. Let's see that.
I feel like I remember seeing that, but yeah, I didn't go through it.
Yeah, resampling dynamic adjustment, RFC 13. Okay. Oh, right. Okay. Yeah, so the resampling thing is so right now, so the default hypothesis updater, you like at the beginning of the program, you set this is how much sampling you have to do for every iteration. It's basically fixed. And what we want to do is with the resampling thing is, when we're talking about resampling is how many hypotheses are we testing? And so resampling means, do we add the new hypothesis to this hypothesis pool, or do we remove some hypothesis from the hypothesis pool? And right now, that prior to this there was a fixed like ratio of old hypothesis and new hypothesis, and it was just always constant. But the thing is, but this means hypotheses come from like unlikely things, but they'll still get computed and tested, etc., because you have a fixed hypothesis pool. The resampling means we want to stop computing hypotheses that are very unlikely, and we want to sample more hypotheses from the object that we think we are actually on. So for example, if I'm looking at a cup or a potato, and well, if I'm trying to decide behind a cup and a potato, I'm going to have like maybe 50-50 split of cup points and potato points that I'm sampling. But as I'm doing on the cup and the evidence for the cup grows, I want to get a more fine-tuned sampling of the different cup rotations and other things, because rotation is a hypothesis as well. So I want to sample more from the hypothesis about cups and sample less about hypothesis around potatoes. That's where the resampling vocabulary comes from.
My understanding is that you do different hypothesis update operations for each object graph in the LM. So does that mean for like that, if you're doing this resampled hypothesis updater, like whichever is object you want to do more, you just set that one to use more hypotheses in its update step, and then in the separate potato step, you just reduce the number of hypotheses that you're looking at, but they're still like separate calls to like the hypothesis updater, right?
I think so, but I don't know the answer to that. I don't know enough.
It's just my understanding, at least from the older version of the code that I was implementing this in. It seemed like every object graph is processed separately, like independently. Gotcha. And even in this case, like when I was shifting away from doing all LMs at once in one kernel dispatch, I was still going to try to have all objects for one LM run in one stacked kernel. So, I mean, I think nothing you said so far makes me think that wouldn't work for the resampling one. Just conceptually, I want to make sure I understand whether object graphs are processed separately in the existing code or not.
I don't know if this answers it. This is what I'm looking at. So one thing that's new in the resampling hypothesis updater is inside the update hypothesis. This is big enough. Here. So resampling update hypothesis. These are the relevant bits, right? Existing hypothesis, informed hypothesis. So these will choose hypothesis based on what's going on. Versus this does not occur in the default one, as far as I recall.
Okay, and this is still happening per object graph. Like that's what the graph ID is there, right? Sample informed.
That is an object graph.
Yeah, is called separately on each object graph.
Yes. Oh, okay. Is this the answer to your question?
Yeah, I think so.
So that's the because the API here is So update hypothesis is called per object graph. Just at the API level, if that answers.
And so this just adds some overhead at the beginning to do some thoughtful adjustment about which hypotheses from that object graph we're actually going to consider and do updates for.
Yeah. Return hypothesis updates.
I'd have to look into like how the sampling operations work to see how easy that would be to do that on GPU as well, because we wouldn't want that to go sequentially either, right? We'd want to be able to do that in a batch.
Let's see. So this is the sample informed and sample existing. So sample specimen. I think this is just like a array operation. I don't think there's much happening here.
Okay.
Calculate, keep, and remove IDs.
Yeah, I mean, like
calculate slopes. This is looks like a NumPy matrix thing.
Yeah, the big thing for identifying like what easy versus a pain for the GPU is how much does like one value depend on all the other values, right? So like if we can, if we have a big list, but everything, each index is being processed completely separately, it's like phenomenal for GPUs. Whereas like KNN is annoying for the GPU because it actually matters what the other ones are, and you have to synchronize between them and all that. So I don't know. Seems like this might be pretty straightforward. But.
So that might help, right? And then it's like, but I don't know if the default hypothesis updater uses that. So tracker dot, it doesn't even use a tracker. It's not a thing. So this is what I'm talking about. Is like I think this is the future, and so I think if you're gonna bother with the GPU, I think it should be the resampling hypothesis updater.
Okay.
Because this is too rigid. Like we definitely don't want. I would just say like right now do this unless like I come with counter evidence, and I'll confirm it for you. But like I think this is the one to care about.
Yeah, well, I'll take a look at it, see
Okay.
how much that would change things.
Yeah. Okay.
Yeah, so like in terms of next steps, it seems like we still probably have some more digging and discussions to figure out the API and the way that we want to integrate these backends. We're doing these graph groups and things like that. What's most helpful for me to start working on for the backend? So like I want to look into seeing what it'd take to make kernels for the resampled hypothesis updater operations.
So I would think do that, and I'll try to change the API on the Monty side of things for the grouping thing. See what the grouping API would look like, because I don't need GPU expertise to do that. Versus like you could do that, but it's like that's not helpful. So like let's say Jeremy or I can look at that.
Okay.
And then we'll. So I'm trying to think. So we actually have from this thing. So we kind of talked about the scope. So it's this part, this and this. So actually, this we're talking about. This is resampling. Actually, talking about resampling hypothesis updater. And then this will be resampling. But then the other part is so there's another thing that so we're missing a thing here. So this is a refactor for parallelism. Factor into a grouping call. Like that makes sense to me right now. I don't know if I read it tomorrow if I know what that means.
Yeah.
But what am I trying to say? Can you help me? You know what this says.
Wait, what are you trying to say?
So the hypothesis, so I'm thinking this is the stuff we talked about where it's like it's the grouping call at the high level that was not at all helpful to the GPU conversation. This refactor the hypothesis updater to support multiple backends. This is actually the helpful part. Resampling hypothesis updater to support multiple backends. This is the thing that I said I can do because I don't need GPU expertise to do the grouping bit. This is refactor step learning modules to use grouping.
Yeah, like grouping of LMs.
Of LMs.
Whether that's just one LM per group or larger groups. Like that's from the experiment side, that's what it wants to see. It's just groups of LMs and then we feel good about sort of this, at least for now, the kind of simple, just like, dispatch.
Collect.
Yeah.
So absolutely.
That should work fine for the groups. And then the backend can kind of handle whether it's a group that gets stacked into one kernel dispatch or just an LM.
Yeah.
Where we'll stack across object graphs. So yeah, we already have to figure out some of the stacking.
And so
anyway, it's just whether we go across LMs or not.
And then, and there's not a clear path between this and getting to the resampling hypothesis. So this is agnostic of the backends, basically, is what I'm trying to say. And so this is like an independent thing.
Yeah.
Like I'm like, what depends on this? Like nothing depends on this.
That's great.
Right? I mean, technically.
Yeah,
because if you do the resampling hypothesis updater, then it's just cool. We can still run it in a for loop, and it's going to be terrible, but it still will work. Like it will still run on the GPU, but in order to help with that, this step. That's the question. So this is breaking. That's okay. So now I have a code question that I know the answer to is but we're out of time. The question I have is hypothesis update called per LM? Like, is there a clear linkage between the groups and hypothesis updaters, or is there like another loop inside an LM hypothesis update?
Yeah, so right now, every LM has its own hypothesis updater.
Yep.
But it calls it separately on every object graph in the LM.
Thank you. Thank you for that.
Yeah, and already we want to shift it for definitely the GD backend where it's doing all object graphs at once within an LM. And then stacking the group is now would be do all object graphs across all LMs as one kernel dispatch.
So that's still to be defined then, that part of the API. Is that true? Or do you have a clear idea of how you want to do it?
Yeah, I think that I think there's still some details. I mean, it's internal to the LM, right? Because I think in the server side, like it's just whether it's calling a dispatch on a group of LMs or on the LM itself. But then inside the LM, how it calls into the backend and how we do the stacking, whether it's across LMs or not. Like, I think there's more to figure out about that.
Am I saying the right thing? Define how LM to object to hypothesis object graph. Define how LM to object graph to hypothesis updater call should work, right? Like this is hypothesis updater. You're confident we got this. We kind of confidence we got this, but then we're still missing the LM, the path through the object graph, how the object graphs are getting. We're missing the AP, we're missing the definition, the clear definition of an API where stuff gets parallelized across object graphs. This parallelizes across LMs. This parallelizes across hypotheses. And we want to parallelize it across object graphs, and we want to parallelize across hypothesis update call, which is the same thing. Parallelizing
and
object graph. Okay.
Important to say that in order for this CUDA streaming approach to work, I think how it works is we'd have one backend object that's shared between LMs because it needs to be, it's like one backend that's handling those streams and running them across LMs and then being able to like report back when all streams finish, right? Like you just want one call to one backend and not have to like go ask every LM whether it's done. And so also then across groups, like is that one backend across? Yeah, because the groups also call into the dispatch the same flow. So yeah, it's still one backend. And then every group or / every LM references that same backend object. Does that make any sense?
It probably would, but I'm also feeling like time pressure that should be done. And so when do you want to meet next? When is good? I'll just send you a schedule and then see what we can do if you're willing to meet next. In the meantime, while we figure this out, I think I can at least attempt some progress on the refactoring bit, and then this is still a big unknown. And then I think so next on the agenda we'll be trying to figure this out. Does that sound reasonable?
Yeah. And we can talk over the discourse and sometime early next week or something like that. Be fine.
Okay, awesome. Well, thanks. This was
it's really fun to actually finally get to talk about it. It's been a lot of me just like reading documentation and like I think this is right, but I'm not really sure.
Sounds good. I'll also see if like if I can drag Vivian into this too, because that will she is the expert on that stuff, so that will that should help tremendously.